Good morning, QCrypt, and apologies for not being able to present in person. And at the same time, a big thank you to the local organizers for providing this opportunity to nevertheless give this talk online to you. And after that, I think I get started. Today, I'm going to talk about the framework for the security analysis of practical high-dimensional QKD setups, which is a joint work with Markus Huber. And I start with a brief motivation. QKD, once we want to overcome distances which are typical for modern urban areas, we use satellite links. And free space and satellite links, however, are usually severely limited by noise. And when I talk about noise, I usually refer to sunlight, which for many platforms limits operation times usually to nighttime, which is quite restrictive and which we want to overcome. On the other side, research on high-dimensional entanglement has been shown to enhance the noise resistance in entanglement distribution tasks, while at the same time obviously increasing the key rate per coincidence event. There are plenty of experimental platforms available, such as time bin, frequency bin, and orbital angular momentum. And there's a rapid development in high-dimensional photonics. So the question is, why haven't we been using high-dimensional QKD way more often? And the answer is simple. While experimental progress has been quite quick and breathtaking, it always felt like theory is kind of lagging behind. In more detail, there has been no security analysis available for practical setups. The existing analytical security tools usually relied on practically infeasible measurements. What do I mean by that? Usually mutually unbiased basis measurements, which cannot be carried out on many of the practically available platforms. On the other side, purely numerical convex optimization methods can deal with the measurement capabilities of current setups, but they're usually computationally too expensive and can't reach the dimensions we're actually aiming for. Additionally, in the end, for practical security, we need a composable finite-size security argument, which wasn't available so far. Our goal is to bridge this gap by providing a semi-analytical method to unlock high dimensions. Okay, let's get started. How did we achieve that? Our starting point, at least for now, I talk about the asymptotic setting, was the famous David-Winter formula, where we quantify the key rate as a difference between two entropic quantities. The interesting term is the first one, which is the von Neumann entropy of Eve, given Eve's side information on the key, which we can lower bound by the mean entropy of X given E. The nice thing about the mean entropy is that we can express it as the negative log of Eve's guessing probability on the key, which then we can formulate as an optimization problem. This primal optimization problem, as I call it here, is subject to constraints of yet to be defined observables and their respective observations, and I'm going to talk about them in a few slides. We then turn this problem into an SDP and apply duality theory and get a much simpler problem. As mentioned, this problem is now comparably simple, and the only major constraint left is a largest eigenvalue problem of a set of matrices which are linear functions of the observables I haven't defined yet. So therefore, it might be time to talk about those observables now. So how do we choose them? We have a few requirements. They should be, as mentioned, experimentally accessible for most of the platforms that are available out there. They should allow a solution without using heavy numerics. And in the end, of course, we want to obtain decent key rates. So let's recap what do we know from measurements on usual platforms. On the one side, we usually know the diagonal of a density matrix from computational or set basis measurements, and we perform some superposition or generalized X or Y measurement, which gives us some or at least some partial information about some off-diagonal. This doesn't have to be necessarily the first off-diagonal, but usually we don't know much about all the other entries of a density matrix. So this is quite restrictive, and it makes it quite hard to satisfy all the 3 points for observables I mentioned up there. So we extend the set of possible operators by applying a matrix completion technique. This technique gives us some partial information about some of the missing density matrix entries. In more detail, we get some lower bounds on certain further off diagonals. We used inspiration from entanglement-witness theory, and I give you intuition now for the example of dimension 3, how we chose those observables. The idea is, ideally, Bob receives a maximal entangled state. So if there is no loss and no noise, Bob would receive a maximal entangled state, which looks roughly like that. So the idea is to cover all the, with our witness, we should cover all the elements that are present in the maximal entangled state. However, in reality, we won't receive a maximal entangled state since there is loss and noise. Therefore, in general, the data quality will decrease. So we know everything about the diagonal and maybe the first neighboring off diagonal, but due to using the matrix completion, for example, we only have partial information about further off diagonals. Therefore, the idea is to choose this witness and weigh the different off diagonals differently. So we associate a certain weight factor with each of the off diagonals. So what we achieved is we moved the problem from finding a witness to finding the relative weights of this particular observable. This is already a progress, but it would be still quite tedious to find the relative weights, for example, manually. So the idea is to split this witness now into d-1 observables, where d is the dimension of the system. And then choose them in some sense orthogonal. Such by orthogonal, I mean that each of those observables accesses a different off diagonal exclusively. So the first, in that example, the first observable accesses only the first neighboring off diagonal, the second one, the second neighboring off diagonal, and so on. This comes with a nice advantage. If we now think back of the dual problem, this is already kind of a simplified version of it. We can include the search for the weight directly into the dual SDP, namely in the search for the dual variables. So we kind of give the dual variables a physical meaning, namely the relative weights of the different observables to each other. So I think now it's time to have a look in how our method performs, and therefore we use a time-bin setup that we analyzed in an earlier work and run a High-Dim-BB84 protocol for illustration. We plot here the asymptotic key rate versus the isotropic noise parameter and compare our work with the works by Sheldon Scarani and Dola and co-workers, where both of them require using mutually unbiased bases or measuring mutually unbiased bases. So if we compare that directly to our method for this platform, the key rate for those methods would be actually 0, since we can't perform map measurements with the platform we analyzed. Therefore, to allow for a fair comparison, we combined their methods with matrix completion to kind of allow a reasonable comparison here. We see that our curves, which are the ones in orange, outperform the work by Dola and co-workers basically everywhere, which is the dotted gray curve, and we perform comparably with the method by Sheldon Scarani in the high isotropic noise parameter regime, which is the low noise regime, while we outperform it in the regime where it's interesting, which is the low isotropic noise parameter, or vice versa, high noise regime. So the second question is then, how do we perform compared to numerical methods? And again, we now use the numerical method that we employed in an earlier work, and compare here the curve, for example, the orange one for dimension 8, asymptotic curve for dimension 8, using the numerical method. And if we use the same dimension for with our analytical method, our curves would be only shy behind the d=8 numerical curve, mainly due to using h-min instead of the von Neumann entropy. But once we go to higher dimensions, which in our case, for example, dimension 16, which is not accessible using the numerical method anymore, there dimension 8 was the limit on my computer, and going to a cluster, the limit was 11 or 12. So going to dimension 16, we already outperform the numerical method for dimension 8. So we have a clear advantage in using our methods together with high dimensions. Okay, let's come to the second part, namely the for practical security, we in the end need composable finite size security. So in the next few slides, I try to convince you that our method is compatible with those requirements. Here I'm not going to give a detailed proof, but only give a sketch. So what we did is we proved the fixed length security against IID collective attacks using the ARENA framework, and then lifted to coherent attacks using the post-selection technique. Additionally, we also applied a recent adaptive length security argument, which enhances practicality, and I'm going to talk about that in a few slides. Anyways, the conclusion is, the nice thing is that all the appearing quantities that need to be calculated in those three variants can be calculated with the method I just illustrated for the asymptotic case. Yeah, let's come to some of the results before we come to the variable length discussion. Again, using the noise model from the earlier work, we plot here the secure key rate over the loss, and we see that the collective attack key rates for example, a block size of 10 to the 10 already reach regions which are very relevant for today's satellite communication. So we can reach distances more than or like loss regimes up to more than 50 dB. Okay, now to come to the last part of my talk. Let's revisit how the acceptance decision, so the parameter estimation in the fixed length finite size security proofs that are composable usually takes place. Standard proofs require the acceptance test to be fixed beforehand. So we need to know the expected channel behavior, or at least we need to estimate it. And based on this estimated channel behavior, we define a set O here in orange. And whenever we run the protocol, we compare our actual observations with this expected behavior. If we're inside the set O, we know how much key we get, and otherwise we have to abort. This is kind of a problem for unknown or even unpredictable channels, which usually is how free space channels behave. There we have a high abort probability. Just assume we run the protocol 8 times, we perform measurements, and this is what we measure. So we ran the protocol 8 times, invested lots of time and effort, and nevertheless, we never hit the set and therefore never obtained key. So the natural question is, can we do better? And the answer is yes. It was given by Devashish Tupkari and co-workers recently. And the idea was to build the security around the observed statistics rather than the expected statistics. And I'm going to show you that our method is also compatible with that. So the idea in the fixed length scenario is the following. Assume now we have 2 observables, then we have to fix our expected channel behavior, build our set O around it, and associate a subset of all density matrices which we associate with observations in that region. Whenever we hit inside, we know we get a key of a certain length. Whenever we don't hit inside, we know we don't get key. So it's a binary decision. On the other side, in the variable length security scenario, we could do the following. We make some observations. We associate a certain set, which is now a function of the observations, with F, and obtain a key of a certain length. When we make another observation, we associate a different set and get a maybe smaller key, but this key doesn't have to be necessarily 0. To illustrate how this behaves with our method, we simulated 2 channels. One is a statistically fluctuating channel where the channel loss and the solar photon rate are normally distributed. And the other one is what we call a rapidly fluctuating channel, where we randomly sample 1 out of 9 statistically fluctuating channel to simulate an actual atmospheric channel. Here I simulated 100 runs and plot the secure key rate over the number of runs and compare the fixed length scenario here with orange or red crosses with the variable length scenario with the blue circles. We see that, as expected, in the fixed length scenario, we either get a key of a certain length or abort, which means we have 0 key, while in the variable length scenario, the length of the key adapts according to the data quality. In the end, it turns out that actually we only had to abort twice, while the data quality would have been enough to generate adaptive length keys in all the other cases. So in the fixed length scenario, we wasted quite some performance. In the end, in that case, this results in, this is what you can see in the horizontal lines, in roughly twice the average key rate in the variable length scenario compared to the fixed length scenario. So what about the rapidly fluctuating channel? Here the difference is even more distinct. Here we get roughly 6 times higher average key rate for the variable length scenario compared to the fixed length scenario. And this already brings me to the end of my talk, and I'm going to sum up. The proofs for High-Dimensio when we started this work so far mainly reported asymptotic rates requiring either unrealistic measurements or excessive time-consuming optimization tasks, which were quite restrictive and limited the performance and the accessibility of High-Dimensio. We developed an effective method that tackles this problem and provides lower bounds on private entropies occurring in QKD. And we also provide a practical, fully composable finite-size security proof, which is quite easy and quickly applicable. One just has to perform the standard measurements, which are native to the platform that one is using, turn them into the observables according to the method I just outlined, input them into our method, and in the end, we obtain a key where the length is chosen according to the quality of the observations. Yeah, thank you for your attention. Please feel free to check out our works, and if there are any questions, I'd be very happy to answer them. Thank you.
Right. Thank you, Florian, and especially thank you that you're here with us at this, what must be an ungodly hour in Vienna now. So, okay, no. I will ask the audience here for questions, and maybe you will see me on the screen, you will hear someone else speaking, which might be confusing, yes. But it is what it is. Questions?
First, thank you for the talk. I just mainly had a question. Why can't you calculate the von Neumann entropy? For example, in DI-QKD, I mean, a lot of work has gone into finding numerical tools, and I was just wondering what's the issue here? What doesn't translate?
We tried the standard methods that were available, and usually the computation time was just too much. It just took way too long, and it just we ran out of computational capabilities before reaching dimensions that were somewhere close to where we wanted to do. I said dimension 8 was kind of the limit for the methods we used. Maybe using different methods, you can go a little bit higher, but unfortunately, most of those problems scale quite unfortunate with dimension. It might be possible that there are numerical methods out there that could do it or can be adapted doing it. At least we didn't find a way of achieving that, and this kind of then motivated us going to analytical methods.
Thank you very much.
Thank you very much for the very clear explanation. I have a curiosity. When you presented the secret key rate, if you could come back to that slide, please. Seems like with your method... Sorry?
The key rate versus loss, or this one?
This one is fine, yeah.
Yeah.
So here you're showing that basically you managed to improve quite significantly with respect to the fixed length key rates. I am curious because I'm not actually an expert. Here you're presenting the bits per coincidence event, just in order to compare it with other setups or schemes. In which regime do you think that this is actually the way to go, the best scheme to actually achieve the highest possible secret key rate, maybe per second or per signal sent?
I mean, I think that's kind of a difficult question, and as you kind of already foreshadowed, I think this has to be analyzed always together with the platform you're using and the hardware constraints of this platform, because we used here a time-bin setup, which kind of means you always have the conflict of using more time for your time bins, so squeezing more time bins into the same time frame, versus using smaller time frames and therefore smaller dimension. And therefore it's kind of a trade-off. So it also depends on how much empty frames you have in this time bin setup. So I think it's not straightforward to answer, and I think there might be other conclusions for example, frequency bin. But in general, I think maybe the fairest comparison is to refer to the curve I presented earlier. This could be like roughly here in, oh, sorry, this again in bits per pair cent, sorry. Then maybe let's go to the asymptotic curve. No, it's again bits per pair cent. Sorry, yeah, then I don't have a plot with bits per second available here. But yeah, I think it's highly specific to the platform you're using, and I think even the dimension has to be optimized with respect to the hardware constraints, because in general, d times log d scales better than log d. So going to high going to high dimensions, at least if you share the same time, we were kind of the time being set up, is only beneficial if you A, want to overcome high noise, or B, only expect very few of the bins to be actually populated. So it's an optimization task on its own.
I see, that's very curious. Thank you very much.
Welcome.
More questions? So maybe a quick one from me then. When you select these observables, you presented an example where you want to use the maximally entangled state. But I suppose if you choose a different state, would a modified version of this procedure still work? Do you have like a sort of machinery that you can just apply? It would just maybe be a little bit more complicated. Did you look at that at all?
Yes. So here I used the maximum entangled state since for the setup we had in mind for illustration purposes, we expect the source to produce the maximum entangled state. So I'd say it always works well if you try to aim for what Bob should receive in the ideal case and construct your observables based on that. So if Bob would expect to receive a different maximum entangled state, then you could perform the same procedure with the according state then, yes.
Okay, thank you very much.